Web applications are the publicly available interfaces that provide connections between end users and web servers. In this module, we'll cover threats to web applications and the popular methodology used for hacking web applications. We'll also discuss several other considerations, including authentication and authorization mechanisms, database connectivity, injection attacks, and other threats to web apps. Web applications are typically thought of as the user interface that provides access to our data or our web servers. That data could be just a website itself, or it could be access to underlying information found in a database. There are various threats to web applications that we need to discuss and understand, and we'll cover those specifically as we progress through this section of the course. But first, let's look at the general flow of how web applications work. Let's say we have a user who is accessing maybe a login form of some sort in their browser. This could be a login to a particular website, or they could also just be performing general browsing without the need for logging in. In other words, maybe they're just visiting a typical public website. These resources are available commonly over the public internet, so users can access this web application from anywhere. We also call this the front end, or the GUI, the graphical user interface. And this is what the user actually interacts with or sees. That is coded in languages like HTML or CSS as a couple of examples. When the user enters the URL in their browser and makes a request, whether that's logging in or not, that request is sent to the web server. The type of request determines what the web server is going to do. If the user is simply requesting a web page, then the web server can process the request and return the appropriate web page to the user. If the user is logging in, maybe they're using a resource that requires login, where they're trying to access a specific database, for example, the web server knows that this request will need to be processed server-side. So this would be forwarded to the appropriate web application server in the network. It's common to have application servers that are separate from our web servers. That's a good security practice. If the user request requires interaction with a database, then the web application server will access the database on their behalf to retrieve or to update information. And the database itself, of course, runs on its own operating system and would use that underlying file system to process the data, and that data would then be sent back to the web application server and in turn to the web server and passed over to the user. So that's the typical flow for web application data. We have two general types of web services available. First, we have SOAP web services. SOAP stands for Simple Object Access Protocol. This has been around for a long time, and it was originally developed by Microsoft. This relies on XML, Extensible Markup Language. This operates similar to HTML in that it doesn't actually perform any actions. It just simply identifies information with tags. So in other words, it just marks up the data, as the name implies. XML was primarily designed to carry data and to simplify the data transport and sharing processes, and XML does store that data in plain text format. SOAP itself was first designed so that applications built with various different programming languages had a common way to communicate. So SOAP is a protocol. And we also have REST web services, otherwise referred to as RESTful web services. REST stands for Representational State Transfer. Whereas SOAP is considered to be a protocol, REST really is more of a complete architectural approach to web services. This is a more modern and lightweight alternative to XML. So SOAP is considered to be a legacy system, although we do still see that used in some places. REST came later on, and that's viewed as a faster, more modern alternative. With REST services, we see 4 HTTP verbs, or actions in other words, used to perform tasks. These are get, put, post, and delete. To understand our threats, let's revisit the vulnerability stack that we previously looked at. Notice our custom and third-party web applications at the top of this stack. As we've mentioned, it's fairly easy to defend against those lower levels. We can implement things like firewalls and IPS. We can have good security features on our routers and switches. Our operating systems and databases should be patched and updated, so those are more difficult points of entry. Of course, these lower layers do have their own issues and they can be susceptible, but generally, web applications are the places we're going to see vulnerabilities in our logic. There could potentially be vulnerabilities in the programming language configuration for the business-specific custom web app that we've built, or in the user interface design itself, and that can also be present in third-party components that we've borrowed. OWASP, the Open Web Application Security Project, is the best resource for learning about web application threats. They have a top 10 list that is a standard awareness document for web application security, and they've gone and assessed the top web application threats in the world. The most recent update to this list was in 2021. So let's talk about this list, and let's talk about what the different threats to our web applications look like. Currently ranked at number 10 are server-side request forgery, or SSRF. This happens when a web application is attempting to retrieve a remote resource from an internal server without validating the URL that was accessed by the user. So that can allow the user to alter the URL in some way, often adding something to the end of the URL, in order to gain access to back-end systems or databases that should not be accessible from an external network. Recent cybersecurity breaches like the Capital One incident actually involved SSRF techniques. Number 9 is security logging and monitoring failures. We've talked about the importance of logging previously and how having ineffective logging or no logging at all can allow attackers to remain undetected and maintain persistence in the network. In 2020, the average time taken to identify a data breach was listed at 228 days. That's a very long time to have someone go unchecked and unmonitored in the network. So historical logs are critical. Number 8 are software and data integrity failures. As an example of this, if you think about your typical home router, many of these do not verify the device firmware when you're performing a firmware update. That is an integrity flaw. That means an attacker could somehow gain access to your router and send their own malicious version of the firmware. This malicious firmware would of course not be signed by the hardware vendor, but if the router isn't designed to verify that, it will be successfully installed. That's a major concern, and it's a growing target that really can only be fixed by proper software design as we create new devices. We're hoping that older susceptible devices are phased out and these newer devices are designed more securely. Number 7 is identification and authentication failures. These are flaws in our authentication or session management processes that would allow for things like automated password attacks, brute force attacks, and so on. This would also include weak, well-known, or default passwords being in place, as well as passwords that may be stored in a weak manner, maybe with weak encryption or even in plain text. In addition, a growing recommendation is multi-factor authentication. So if we don't have a multi-factor authentication method in place, this is considered to be a failure. Number 6 is vulnerable and outdated components. This is fairly self-explanatory. We need to make sure we are updating and patching our software as those updates and patches become available. This would also certainly include retiring any operating systems or any software that is considered to be end of life. Those softwares that are no longer supported with updates or support in general. Number 5, we have security misconfigurations. This includes unnecessarily available ports and services, default user accounts left in place, improperly configured account privileges, and more. Now, these aren't specific to web applications. We want proper security configurations throughout our entire network, but this is definitely a threat to web applications. Number 4 is insecure design. These are based on underlying architectural flaws, and that means that during the design process of the web application, whether we're talking about software or even physical network hardware topologies in our network, we need to have security in mind from the very start. Unfortunately, security is often an afterthought. We try to shoehorn security into our web app design at the end of the process, but this should be checked during the entire development lifecycle. Number 3 is injection. SQL injection probably comes to mind when you think of injection, and that's a common example of an injection vulnerability. If the data that the user is supplying into an input form of a web application is not properly validated, filtered, or sanitized, then the attacker could inject malicious instructions into a web server form, which would allow them to perform actions like maybe reading sensitive data from the database or even modifying and deleting the data. Number 2 are cryptographic failures. Many web applications and APIs do not properly protect sensitive data. Problems here can include data being transmitted in clear text, or even the use of deprecated hash functions. Things like using weak MD5 or SHA-1 hashing algorithms. An example of a design flaw is maybe we have a database that stores usernames and passwords, and that uses MD5 hashing. If this is accessed by an attacker, these passwords can be easily reversed due to known weaknesses with the MD5 algorithm. And the number one threat to our web applications is identified as broken access control. This relates to what a user is able to perform on a network or on a software device, and failures here will often lead to data being exposed to unauthorized parties. We've mentioned the principle of least privilege earlier in this course, and that certainly applies here for good access control. We want to make sure that our users only have the amount of access that is absolutely necessary for them to perform their jobs. Before we dive into specific examples of web application hacking methods, let's outline the steps here from a high level. First, we would want to footprint the infrastructure. This would include performing host discovery on the servers which actually host the web applications, searching for services and ports, things like banner grabbing, and the discovery of hidden directories or content. Next, we would want to analyze the web applications themselves. We do this in order to map out any potential entry vectors, and many footprinting tools apply here as well. In particular, we're looking for vulnerabilities in the underlying technologies or any misconfigurations that will allow access for data exposure. Next is bypassing client-side controls. We're trying to bypass any controls that may be in place which would prevent a user from interacting with a web application in an unrestricted or unexpected way. If we're able to bypass client-side controls, then we have more control over the web application and the data. Next, we would attack authentication mechanisms. Anything we can do to exploit design flaws or configuration flaws which will gain us authentication. This could be password attacks, forgotten password mechanisms, or even the insecure storage of user credentials by the web application and web server. Next, we attack authorization schemes. So even though we are authenticated, doesn't mean that we're authorized to perform certain actions. Maybe we've gained authentication with a typical user account and we want higher privileges. We want administrative privileges. So we think of this in terms of privilege escalation, which we've discussed. We're looking for ways we can get authorized for more access to the resource. The next step is to attack access controls. There may be access controls in place limiting certain users to a particular subset of data on the database, or maybe different levels of access depending on the employee account being used, such as an administrator, a manager, or a typical end user. Again, escalation is the consideration here, and that's what we're looking for. Next, we might attack session management. When a user is validated with a web application, they're given an associated session ID. If we're able to obtain their session ID token, or to mimic one of those tokens, or even to predict what new tokens may be, then we can begin our own session with the web application. Next are injection attacks. We also refer to these as input validation attacks. This can include things like buffer overflow attacks, file injection, and of course, SQL injection. We're attempting to insert malicious strings of input into maybe a login form in hopes that we can use the malicious syntax to control the web application in a way that is unintended. Another thing we would want to attempt are application logic flaw attacks. Most of these logic flaws come from misconfiguration of the coding and the improper implementation of a web application. Again, SQL injection attacks apply here as well, and also things like cross-site scripting. Next, we might target shared environments. It's very common now for organizations to use third-party service providers to host their web applications. So if a particular target is using a third-party service provider, there are likely remote access mechanisms in place that the organization uses to manage their services. So these are something we could potentially take advantage of. Next, we have database connectivity. When a web application sends requests to a database server, there are connection strings being used. In other words, there are strings of data that describe the resource being requested. It's possible that we can alter these strings with malicious instructions in order to perform certain actions. This exploits the way that applications actually connect to the database. Attacks on the web app client is the next thing to outline. If we can alter the behavior of the server-side applications, then we have the ability to affect any other users who may try to access the web application. Common examples here include redirection attacks and cross-site scripting. And one last thing to mention is web service attacks. We're attacking the communication paths for the web services, and oftentimes the goal here is something like a denial of service attack. Now, it's worth noting that this isn't necessarily a step-by-step process where one thing has to be accomplished before we move on to the next. Some of these tactics may fail, while others may be successful. It's also possible that success with one tactic leads us to capabilities where we can achieve another attack step, even out of the order that's been presented here. So this is simply a framework for common methods that we would use to target web applications. We've spent some time already in this course looking at footprinting techniques, and many of these are going to apply to web architecture. There are also things that are specific to web application footprinting. So let's look at a few of these options. Some of these we've looked at previously, like NIC2. If we say NIC2-H 10.0.2.4, in my case, again, I'm running the Broken Web Apps VM from OWASP. And of course, we see the vast amount of information that NIC2 can provide. We see information about potential vulnerabilities that are in place with service versions. We see the versions of the server being used. We see this is using Apache. And of course, we see some different vulnerabilities listed here that points us to CVE listings as well. So this is a tool we can use to begin footprinting and researching. Let's break out of this output. And another tool we may use that we've looked at before is Nmap. So let's say Nmap 10.0.2.4. And this, of course, returns some results regarding some open ports and services that are currently in use on the web server. With this output, we may want to take note of some open ports that could be of interest. Some of these ports could help us do what we call banner grabbing. We've mentioned banner grabbing, where we're reaching out to a server and we're trying to get that to return information about the remote host. That could be the operating system, the software versions, and more. So we do see that this has port 22 open for TCP. So let's use a utility called netcat. And in order to run this utility in Parrot OS or in Kali, we can say NC, short for netcat. And I'll say 10.0.2.4. And after that, we can indicate a particular port number. I'll use port 22 because SSH is open. And you can see that this actually tells us the SSH version, 2.0, OpenSSH 5.3. And we also see that this is a Debian Ubuntu-based system. So we have grabbed a banner here, and we've gathered more information during our footprinting process. Let's break out of this output and talk about another command called wget. That's WGET. So the wget command was created in order to retrieve contents and files from various web servers. It supports downloads through all kinds of different protocols like HTTP, FTP, and HTTPS, among others. So let's say we're trying to capture the HTTP banner of a remote server that's serving an HTTP website. We can use the wget command. We can use the -q option. That particular flag is going to cover up the progress of our output. In other words, this tells it to do this quietly. And if we say -s, this will actually print out the header information of all of our requested web pages. So let's point that to 10.0.2.4. And we'll hit enter, and here we can see that we have likewise grabbed our HTTP banner. We see the HTTP response message here, 200 for OK, meaning that this was a successful request that we made. And of course, we see lots of helpful information, including the server that's running and different service versions, along with things like the date that this was last modified. Another way that we can do this is through a tool called Burp Suite. So let's minimize my terminal here. And in Parrot OS, we actually have a shortcut on the desktop in this particular distribution version for Burp Suite. So let's click that and get that launched. When we open that, we can choose to open a temporary project or we can do a new file. In my case, I'm just going to go with a temporary project here. I'm going to use Burp defaults, although we can create and load our own configuration files. Let's get this up and going. So now Burp Suite is loaded, and one of the main functions that we can use inside of Burp Suite is the proxy function. So you'll see along the top, we have a tab for the proxy, and if we click in that, you'll see that proxy intercept is on. We also have the option to open a browser. So let's open the browser. Let's click this button, and you'll see that this launches an internal browser that actually works through Burp Suite. This is a proxy browser, and that means that anywhere we try and go to from this browser, it's going to be intercepted by Burp Suite so that we can interpret the information being passed between our browser and the target server. So let's put in 10.0.2.4, which is our broken web app server, and let's try to navigate to one of these training applications. Now, when I do that, you'll notice that we have the loading bar here at the top, and that's because these requests are being intercepted. So if we click back into our main OWASP window, you'll see we have a forward button, and we actually have to continue to click this forward button until our website is completely loaded. So you can see here we have an option for a sign-in that's popped up. We'll just cancel out of that. We'll go back and continue forwarding through this in Burp Suite. And of course, we get an error in our website. So once we've forwarded through everything, we can look at the HTTP history and see the history of everything that's happened. So if I click on this, you'll notice that right here in our request data, this is data that was intercepted. We've interpreted a request in Burp Suite, and we've been able to actually capture the banner. We can see things like the directory here, the host IP address. Let's click on a different request here and see what else we've gathered. So you can see we have an inspector on the right-hand side that will give us a little bit more information. We can drop this down and look at some response headers. We see our server, Apache Coyote 1.1, and we see some other basic information. So just a different option for banner grabbing that we have at our disposal. That's using the Burp Suite proxy. Let's close this software out. We'll close all of our windows and we'll look at one other tool here, which is called OWASP Z Attack Proxy. Again, we see this on the desktop, OWASP-ZAP. So let's click that and get that launched. With these options, we're asked if we want to persist the ZAP session. In my case, I'll just say no. And let's go out to my Firefox browser here. And if I actually take my broken web application IP address, as you can see, I've put that into my address bar here, 10.0.2.4, and inside of that, we have various applications available to us. So if we look at one as an example, this OWASP Mutila Day 2, I have that open at a different tab, and this is a sample login that we can try to test against. So this is just one of the tools included inside of OWASP. So let's actually highlight this URL and let's copy that, and we'll try this against this particular application that's inside of my web app server. We'll go back into OWASP Z Attack Proxy, and one thing we can do is an automated scan. So let's click that. This OWASP Z Attack Proxy, by the way, this is one of the most popular free web security tools out there. It's very powerful, and it has great automation features that can help us quickly discover places that are vulnerable. Let's paste our URL inside of this box. Let's scroll down a bit and let's say attack. And once we do that, you can see the attack process here. In other words, it's scanning this URL. It's looking for all sorts of things. It's looking for vulnerabilities. It's looking for any directories that we might have in place and more. So let's give this just a bit of a moment to run. And once this completes at 100%, we'll take a look at some of our results and talk about those. Okay, our scan is now completed, so let's take a look at some of the things we found. If we look here at the bottom, we have an alerts menu. So if we click on that, this is going to show us all kinds of different alerts about the target. So for example, if I expand this vulnerable JavaScript library, this shows areas where JavaScript has a particular vulnerability, and it outlines some of the reasons why. This is JavaScript version 1.3.2, and we can see the details about how this was found and how this was automated. Let's go and look inside of X-frame options. We see the header is not set, and so on. We see lots of alerts listed here. We see private IP exposure. If we look at this and drill down into that, we see the private IP addresses that are being shared here. So lots and lots of information that we can find. We can also use this to do something called spidering. Spidering is automatically discovering hidden contents or directories. And if we look under our spider section, look at all of the different URLs that were found. In fact, this says 813 URLs have been found. And if we scroll up through this list, they're obviously going to be numerous because this particular web server that I'm using does have many applications built into it. You can see our robots.txt file that we talked about earlier in a different video. We see a sitemap.xml file. So lots and lots of information here. Z-Attack Proxy is a very powerful tool. So these are just a few options to mention for footprinting web architecture. Again, some of these that we've looked at are more specific to web applications, and others are more general and they're going to get us started, like Netcat and Nick2, as well as Nmap. When we're analyzing web applications, some of the things that we're trying to do include checking for server-side technologies and their versions, checking for server-side functionality as well, and trying to identify any files or directories that may be available. This helps us to map out the actual attack surface and any potential entry points. So let's look at some examples of this. One thing we can leverage is Nmap. Now, we've looked at Nmap from a practical standpoint in several places already throughout this course, but I want to point out some included scripts that we have in Nmap for achieving certain goals. So let me pull up the actual folder for those, and the directory, as you can see here, it's under user, share, Nmap, and inside of the scripts folder, inside the Nmap folder, we're going to have a list of Nmap scripts. So these are already defined functions that Nmap has the ability to do. And as you can see, there are a long list of these scripts available to us. Now, one example of a script that I'll point out here is this http-enum. So as you might guess, this can be used to actually enumerate HTTP. So let's give this a look and let's see how we can achieve this. If we jump into our terminal here inside of Parrot OS, let's say nmap-sv, and let's say -- script, and we want to say equals, followed by the actual name of this script. Again, I'll pull that up just so you can see that. It is http-enum. So we'll say http-enum. We will enter a space, and then we can target our host, 10.0.2.4 in my case. I'll hit enter and we'll get this up and going. Again, this is one of the scripts we can leverage in Nmap. We've already looked at using Nmap for enumerating services and ports, but there are many other functions of Nmap that will enumerate many more things. So this should pull up a list of maybe directories and files that are found at this location, which is our OWASP web server. So this could take just a while, so we'll come back when this is all complete and take a look at our output. Okay, our Nmap scripting process is now completed. You can see this particular process took 73 seconds, so that's why I paused the video here and jumped back in at a later time. But if we scroll back up through our results here, we're going to see some potentially exposed files and directories. So we can see all of the directories that have been enumerated on this server, things like /WordPress. There's a WordPress login page because this particular web server from OWASP does have a sample WordPress login page built in there. We also see things like potentially interesting folders with directory listings. We see a folder called /icons. Similarly, /images. So if this were an actual real world web server, these could be directories that might be of interest to us. Let's scroll down. Some other potential interesting folders we see is a directory for documents /docs. Again, we see some of the same information that we've already seen with our previous footprinting steps, like the Apache version listed here. We see a possible admin folder. We see a CSS folder. Again, more image folders, and so on. So this is one option for analyzing the web application to discover hidden directories or hidden files, hidden in the sense that they may not be visible directly from our website input, but now we know they're there and we can begin to try and attack those. So another option for this is a utility called GoBuster. GoBuster is also a directory scanner, and that will allow us to try and enumerate hidden files and directories. To use this, we can say GoBuster. This utility is included already in Parrot OS, and one of the options we can use is dir. This will try to essentially brute force directories. We can say -u to indicate a target. That's going to be 10.0.2.4 in my case. And we want to identify something called a word list. Now, we've looked at word list in regard to password tools already. We've talked about those, and there are also specific word lists already built into Kali Linux. Let me go back into my file explorer here, and you'll see there's a directory under user share word lists. And let me go back into that word list folder. And from here, we have different folders of certain word lists. There's an mmap word list. There are word lists for Metasploit, and you can see those are quite numerous. Those are going to contain things like common usernames and passwords. Let's go back, and we have one for dirb, for dir busting, and the one I'm going to use here, just as an example, is common.txt. So let's open this up and take a look, and you can see that this is going to contain some common directories that we might see on a typical server. Let me close this out. So this is what we want to reference. Now, we want to reference this entire path when we're using GoBuster. /user /share /word lists /dirb, and the name of that file is common.txt. And I forgot my word list flag. You'll notice I got an error when I hit enter. So I actually need to preface this directory with the -w flag. Let me put that in, and then we'll hit enter. And here you can see this is brute forcing everything that's in that common list of directories. Now, you don't have to use this built-in list. You can, of course, curate your own lists. You can find examples of those online, and those could be more helpful than what we have here. But we do have some hits. You'll see that everywhere we had a match, we have a link that's been generated here. So let's click that. And if we click that link, it actually opens it in our browser so we can see the contents of all of these directories that were found. So several of these were in place, several of these common directories, things like PHP admin. There's a WordPress directory, of course, because this does host a sample WordPress site. So that's another option for enumerating directories that will help us to analyze our web applications. One more utility that I'll mention that can thoroughly scan web application technologies and the web server itself is a tool called WhatWeb. This is also built into Parrot OS as well, and we can run that by saying WhatWeb followed by -v for verbosity or verbose mode, in other words. And for the target, let's go back out to our sample site that we've looked at previously here, and let's copy our URL. We'll jump into our terminal and we'll paste that inside and hit enter to get this up and going. This shouldn't take too long to run. This should complete fairly quickly, I believe. And once it does, we'll scroll to the top of our output. Looks like we're all set. So we'll go back up to the top here where we started this output. And there we go. This is the beginning of our output. And we can see various things. We see, of course, various software versions. We see a 200 status where we made an HTTP request to this server, the IP address, of course. We see a summary here of some different versions of software that are running. If we go down into the detected plugins section, we're going to see things like, of course, Apache that we've mentioned. We're going to see an HTTP server header on down here. We see that the operating system is Ubuntu Linux. We can see OpenSSL version 0.9.8. We see the PHP version that's here, and lots more. So this is very thorough for analyzing a web application. So these are just a few options of how we would continue to analyze these web applications. So this is similar to footprinting somewhat. We're using similar techniques, but we're trying to go deeper. The goal here is to try and discover underlying server-side technologies and their versions so that we can help identify anywhere that we may have vulnerabilities. And also additionally, to try and identify any hidden directories or files. This serves a couple of purposes. Number one, we can maybe have immediate access to a potential directory to gain valuable information or data, whether that be usernames and passwords or maybe private financial information. Also, it's going to inform us about where we might want to target our attack. If we can find an interesting directory, that can let us zero in on a specific place that we may want to continue trying to access. Bypassing client-side controls essentially means that we're trying to circumvent any controls that may be in place which would prevent us from interacting with a web application in a restricted or unexpected way. If we're able to bypass client-side controls, then we obviously are going to have more control over the web application and the web data. So let's look at a simple example of this. If I open up my browser here and we go out to my OWASP instance at 10.0.2.4, we can scroll down a bit and you can see that we have several training applications here. The one I'm going to point out is this Mots-clés 2. So let's click that and it will bring up our Mots-clés window. So Mots-clés, by the way, that is one of the many free open source web applications that are included in OWASP that we can use for testing. You can also download this as a standalone tool if you'd like, along with all of the other tools that we find bundled together here with OWASP. So to start with, let's go on the menu on the left. And these menus are going to contain all kinds of essentially different labs that you can do. These are different lab tasks you can perform. Let's go under Missing Function Level Access Control, A7, and let's choose Secret Administrative Pages. So in this case, we're trying to see if we can view a hidden server configuration page. The client-side control that is being assumed here is that we don't have knowledge of the URL for this hidden resource. In other words, we don't know the URL at which this server configuration page is stored. And if we don't know that, we should not be able to access that. Let's see what we can do about that. So in this particular example, we're trying to find any hidden configuration files, and specifically here, we're going to look for a PHP configuration file. The PHP configuration file is read when PHP starts up. If an administrator has left this file in an accessible directory, and they're simply assuming that the average user will never be able to figure out the URL, so they should never see that configuration file, that might be partially true, but this is still a mistake. It's true that the average user won't stumble upon this file, and using the typical functions of the web application should not allow us to view that. But we do have ways to bypass these types of controls and to find this page. To do that in this instance, let's minimize this window for a moment, and let's open up Burp Suite. Burp Suite is a tool that we've already looked at. So just like we looked at before, we'll use a temporary project. We'll use our Burp Suite defaults, and we'll start this up. And just like we looked at before, we're going to use our proxy intercept feature here. Notice our intercept is already on. We can open a browser up to start intercepting our traffic. So let's go back into our Mots-clés and let's grab this address. We'll copy this URL and we'll go back into Burp Suite. And inside of our proxy intercept browser, let's paste this inside. We'll hit enter. And just as we did before, notice the site is loading. So we do have to forward through everything. And then we are taken to this secret administrative page that we've already looked at. This is the page for the lab itself. Now let's go back into Burp Suite itself. And let's take a look at some of the traffic that was captured. If we look at our HTTP history, we can see the information here. We can see the raw file, and we see the page secret-administrative-pages.php. That is, of course, the website itself. If we look at that in our browser, you'll see that is the extension that is for the page address. So what we can do here is we can use a method of attempting to brute force the website addresses. If we actually, in this request side, if we right click in here, one thing we can use is something called the intruder. The intruder function is a tool for automating custom attacks against web applications, and we can range from doing things like brute force guessing to even active exploitations. So let's choose send to intruder, and along the top next to our proxy tab, we have an intruder tab. So let's click on that and take a look at what we have here. We can see the initial configuration details for the target, which is our host 10.0.2.4. If we look at positions, this is what we actually sent over into the intruder. So if we're going to try and brute force this, just like with a brute force password attack, that means we want to insert many different values into this. And in particular, we're going to look at this get function at the top. This is an HTTP verb, and we're getting this page that is equal to secret-administrative-pages.php. That's the example that we're using. That's the actual site, once again, that we loaded up here. So if we go over here, and you'll notice that this has the option to clear on the right side. At the moment, this is actually highlighted in green. If we clear that, that's going to load the normal URL extension, secret-administrative-pages. Now, if we want to add a certain place where we're going to insert payloads, let's say we want to automatically run through a large list of PHP page names or potential PHP page names. What we can do is we can highlight this particular area and we can click add, and that looks just as it did before. It did automatically recognize that, but I wanted to show you specifically how you could choose areas for your payloads to be inserted. So we have our payload position. This is where it's going to be inserted at. Now we need to configure our actual payloads. In the next tab, you can see we have the option to either load a list. We can load a simple list, which would be a text list of payloads, and we can find those again many places online. We can curate those ourselves. In our case, we're just going to manually add a few of these. So let's say secret.php. Let's try admin.php. And each time I am typing one of these out, I'm just hitting enter to insert that. So we are essentially creating a list of payloads. I'm going to make a couple that don't work, just so that we can see how that functions. Now we have 4 payloads in place. Again, these have been loaded manually, but if we wanted to, and for the best rate of success, we probably want to use a large list that we've curated from somewhere or downloaded from somewhere. So all that's in place. We have our payload position, and the way this is going to work is each one of these payloads is going to get pasted into this URL. So first, it's going to insert secret.php into the page equals area. Then it will try admin.php, wrong.php, and notits.php. So this is an automated manner of trying to brute force looking for this. So let's click start attack, and let's see what happens. We do get a message because this is the free community edition that is included for free within Parrot OS. We do have some functionality disabled, and the attacks are time throttled, so I'm not surprised by that at all. That is definitely a function of the free version. So if you do need higher functionality or more features unlocked, definitely check out the pro version of Burp Suite. It's a great tool. So I'm going to click OK, and we'll let this do its thing. And now you can see the indicator at the bottom telling us we're finished. One thing I recommend here is probably sort these by the length. The longer the length, the better chance you have of actually having a legitimate result. So let's click on this top one and let's go over to the response side. This is what has been returned back to us. And let's choose render. And this is going to show us an example of what this actually looks like if we go out to this page. And so you can see that, of course, this one is page not found. If we go to not it, let's see how that loads up. I expect that to be exactly the same, so I'll probably actually skip over that. And let me sort by the longest length at the top. If we look at secret.php and we give that a chance to render, we can scroll down in here and look what we found. We've actually found our secret PHP server configuration page. We found that by trying to brute force the address, and we've discovered a URL that we should not have had access to because we had no reason to know that URL. And you can see all of the valuable information that we can find in this configuration file. So this is one example of how we could bypass client-side controls where we're not expected to be able to do an action, but we figure out a way to do that. That can also include things like cross-site scripting or discovering hidden input forms that may be on a website. Let's look at some attacks that we can do against authentication mechanisms. These are going to include things like brute force password attacks, dictionary password attacks, and username enumeration. Now with username enumeration, we're going to look at an example of this once again using Mots-clés. So if I go back out to 10.0.2.4, which is my OWASP web application, and I go to the Mots-clés 2 page, under OWASP 2013, we can look at broken authentication and session management. And under there, we have username enumeration. So there is a sample login form that we can test this against. So with Mots-clés, when you provide a valid username and password, you're obviously able to log in. However, if you provide an incorrect one, and we click the login button, we have a message letting us know this account does not exist. So that is bad web application design. This essentially tells us that, nope, you got the username wrong. Don't use this username. So as attackers, that's valuable information. Now it appears as though we have a way that we can authenticate whether or not a particular user exists in a database. So by monitoring web application messages, we can essentially know whether or not a username is valid. Now, one basic thing that we might want to do is first, from our actual browser, we can right-click in here and view the page source. So let's see the actual underlying code of the web application page. So first, let's examine this, and I'm going to say Control F to perform a search. And I'm going to look for instances of authentication till I see something that might be of interest. And already we see something of interest here. You'll notice that there's a variable outlined here called authentication attempt result flag. So we're essentially looking right here at the underlying code that's saying if we attempt to authenticate and the username does not exist, we should see a flag of 0, which is what we saw in our actual browser window here, and a message letting us know the account does not exist. We can assume that if it does exist, we would see an attempt flag of 1 here. So not super helpful, but that does give us a bit more information. So what we can do, we can go back into Burp Suite that we've been taking a look at, and we can look at this through our proxy browser again, and we can try and capture a request. This is one method that we can use to try to enumerate our usernames or try to brute force our usernames. So let's grab our actual link here to our login page. Let's go to Burp Suite and let's start our proxy. As we've been looking at, we'll open our proxy browser and we'll paste this in there. We'll hit enter. We will forward through our requests until we get to our sign-in page. So back in Mots-clés, let's try our credentials. Once again, we'll try and log in. We'll forward through this particular area on our intercept tab. Of course, we get the same message that we saw previously. Account does not exist. And let's take a look at our intercepted captures here. So we see our post message. And if we scroll down in here, you'll see the username that I entered listed at the bottom, which was none. And the password that I entered was none as well. So let's right click and let's send this to intruder. We'll go to our intruder tab. And just as we've looked at before, we can set certain positions for our payloads. So we're going to try to load a list of usernames here and try those against this website login. Now, in the previous video, I mentioned how we could clear these payload positions. You'll see that several of these have been recognized, but we don't want to insert our usernames into all of these locations that are outlined in green. So let's hit clear. The only one in this case we're going to give a try is the username box. So where it says none, we'll double click that and we'll click add. Now we're ready to set our payloads. So over here in our payloads window, if you remember previously, we just manually added a list of payloads in here. And I also mentioned that for the most success, you probably want to load a list of these. So let's do that. Let's click load. And if we go under our main file directory structure, we happen to have some under user, share, and inside of this share folder, we can find the word lists directory. And these are where we have some built-in word lists inside of Parrot OS. So let's look at Metasploit, and you can see all of the lists of built-in passwords and username files for Metasploit. So let's look at HTTP default users. Here we see that TXT file. We'll say open, and you can see that that loads our text list into the payloads option. You can see all of those now inside here. So now we're ready to start our payload. We have 14 payloads. I'm going to click Start Attack. This will take a bit of time, so we'll jump back in once this is all completed. So now you can see our process is finished, and we can actually start looking through the results for all these. We have attempted to enumerate users here. So for the user name security, if we take a look at our response, let me go ahead and maximize this so we can see that a little bit easier. We're going to see what that returned to us when we had security as our username. We'll scroll down, and of course, we see the same thing we saw previously. Account does not exist. So we know this isn't a valid user. If we look at admin, however, and we let this load, let's scroll down into that window, and this time we see a different message. Instead of user does not exist, notice we see password incorrect. So this clues us in on the fact that this is probably a valid user. Let's go back into Utility here, and let's try admin. We'll try a password here, and we do see the same message from our main web console. If we actually right click on this, view page source, we'll do a Control F to search for authentication, and this time we see a flag of 1 just as we suspected. So we see a variable for 1 letting us know that this is a valid user. So that's one way that we can enumerate users on a web server. And we can actually go through the exact same process for passwords as well. Let's minimize all of this for just a moment. And of course, as we've looked at previously, it's also possible to do this with the terminal using tools like Hydra. So let's maximize our terminal here. And I'm going to change into the directory user, share, word lists. And we'll do an ls command to see what we have in here. Let's go under Metasploit. And here again, we see all of those text documents available. So let's try Hydra in the same manner. Let's say Hydra. We could say -L. And the list we want to use, we'll once again try http://default_users.txt. So that indicates our user word list. For passwords, let's say http://default_pass.txt. And as an example, let's say we wanted to try and attack SSH for this same server at 10.0.2.4. We can hit enter, and it looks like we have a socket error. The connection is closed. Let's try FTP as well. So now it's trying to attack the FTP service to see if any of these default usernames are in place, and we would continue this process. This is just a different option outside of Burp Suite for being able to do that. So again, we're essentially trying to attack authentication mechanisms, whether that's through enumerating users, brute forcing users even, or using password attacks to try and gain access. Next, let's look at attacking authorization mechanisms, and we think of this typically in terms of privilege escalation, a term that we've discussed previously. We're looking for ways where we can get authorized for more access on the resource, and many times this happens from a normal user account. Maybe we've gained access through user enumeration or through password attacks to a typical user account. Authorization mechanisms, by attacking those, this can allow us to escalate our privileges, hopefully to those of an administrator account. So if we take a look here, we're in our Utility, we're at the main login window, and there are several built-in logins by default that you can find in the Utility documentation. One of those happens to be the username John, and the password is monkey. So if we log in, you'll see we have a status update. The user is authenticated. And if I close this out, you can see the logged in user is in fact John. So using this information, let's take this into Burp Suite. Let's minimize our browser here. Let's launch Burp Suite, and we'll take a look at this once again using our proxy intercept to see if we can find any way to escalate our privileges. We'll start a temporary project. We'll use our burp defaults. Let's go back into Firefox, and let's go and log out and go back to our login page so that we can grab this. We'll copy our URL, and we'll use that inside of our Burp Suite proxy. So we want to go to the proxy tab. Intercept is on. Let's open our browser. Move this over just a bit so that we can see our forward button. And I will paste this URL inside. Going to forward to that URL. Let's go ahead and log in using credentials that we already know. Username John, password monkey. We'll log in, and of course we're going to need to forward through this as well. And we do get logged in. We see our authentication here from our Burp Suite browser. So let's go into our HTTP history for our proxy, and let's start seeing what we have in store. So we see our GET requests here where we're trying to access the site, and the one of interest probably to us is this post request. We see that it was posted, the login page, and just below that we have a GET request here too. And if we look inside of our data, the interesting thing we see the username listed here, John, and we see a PHP session ID as well, but really of interest is UID. Now I would assume this to be the user ID, and we see that that's just a normal numerical value. How can we test this out? Well, we can right click in here and we can send this to something called the repeater. We have the repeater tab here at the top. So the repeater tab is going to let us manually try some things, manually try and change this code, in other words, and then it will send that out and see what happens and show us a response. And we can do that over and over and over. It's much easier to do that through this repeater tool than to try to do that manually. So for example, the code that we just sent in there, if we say send, and we send it exactly as it is, this is our response window, and we can see the raw code response to that. If we click render, this is going to render a view of what the website looks like once this is sent over as a GET command. And of course, what we see is status update, user authenticated, and we see the logged in user is in fact John. Now, let's say we want to try to escalate our privileges. One of the first places we would likely try this UID, it seems to be a very simple user ID. They haven't used any randomness in there. Let's just try to change that to a different value. Let's say 4. So we changed it. We can click the send button again. We'll send that in to our repeater, and we see our response window. It's rendered already. And what do you know? We see a different logged in user now. We see a logged in user named Jeremy. So it does look as though these are just single digit numbers. Let's go all the way up to 10 and let's send that and let's see what happens. And yes, it does eventually render. We do see another user. Let's go to, let's say 50. Let's send 50 over there and see what happens. Now, when we send 50 over there, we actually get the exact same user that we saw previously. So we've gone higher than the actual user ID available. So this is a way that we can actually figure out the size of the user and password database that is on this machine. Let's say we go all the way down to user ID 1, and let's send that over. By the way, notice we're not changing the username here in the code. We're only changing the user ID. So if we send that over, now look what we've got. We're logged in as the admin. We've got access to the admin account, so we have effectively escalated our privileges. So if we actually go over here in our request side and we right click and we say show response in browser, this is going to give us a URL that we can copy. We can go into our proxy browser. We can paste this in here. This is going to reference Burp Suite, and that's going to display this inside of our proxy browser. You see we have the status updated message. It tells us we're logged in as the admin. The logout button is available. So we have effectively escalated our privileges to that of an admin account on this web server. In other words, we've bypassed the authorization mechanism that's in place, although that is admittedly weak in this instance. So again, if we go back into our proxy information, we look at our HTTP history, these GET requests and POST requests, these are going to be valuable places that we can find information that may aid us in escalating our privileges and bypassing these authorization mechanisms. Now, there are, of course, other methods for doing this, but this is a simple example that I wanted to show you so that you could understand how this might work. Next, let's look at bypassing access controls. There may be access controls in place, and there should be, in fact, that would limit certain users to a particular subset of data, especially if we're using a database where we're serving information out to users. We don't necessarily want every user to be able to access every piece of data. So this is a very common thing that we would see in place with a web application. Typically, this is divided up by the amount of access that the employee needs to do their job. So an administrator obviously would have access to more data than a typical end user would. So we can think of this generally as a different type of escalation attack. We're looking for a vulnerability that will give us access to the controlled information that we're not able to see with a typical user. So here we're assuming that we've already used some tactics and we've gained access to a legitimate account on this system or on this web application, and we have some login credentials, but we don't have the access that we want. Now, the first thing I want to show you here is we've been working inside of Burp Suite for most of these tools. Again, it's very powerful, and we will continue working with that here. But we've been working with our proxy browser. You'll see Intercept is on, of course, and we can open the embedded browser. But I want to show you how you can actually attach your actual external browser to this Burp Suite proxy. So here I have my instance of Firefox. This is already included with Parrot OS. So if we actually go into our hamburger menu on the right, we can go under our preferences. And if we scroll all the way to the bottom here in Firefox, we have network settings. So this will configure how we connect to the network. And one thing we can do is we can manually point this to our instance of Burp Suite and proxy all of our typical browser traffic through Burp Suite rather than using the internal Burp Suite browser. That might be preferable to you, especially if you're doing real-world assessments. And the way we do that is we select a manual proxy configuration. You can see that I've already had some settings in place that I've used, and these are relevant to Burp Suite. We use the address 127.0.0.1. That is the HTTP proxy. That is the common address for a loopback interface on a system. So in other words, we're routing all of this traffic rather than some proxy server that may be on the internet. We're routing it through this local address, which is controlled by Burp Suite. And the common port that Burp Suite uses by default is port 8080. So these are the settings you want to put in place. You want to put in 127.0.0.1. You want to make sure that's using port 8080. And it's also recommended by Burp Suite to select the second option to proxy all of our traffic through there. So depending on your actual version of Firefox, it may say to allow all traffic, or it may appear, as you see mine here, to also proxy FTP and HTTPS through this. And if we scroll down, you'll see that we have an option to deselect proxy. So if we have particular places that we don't want to proxy through there, you can see some examples here. So if, for example, we put in google.com, that means if we go to google.com, it will not proxy that through our Burp Suite browser. So we can essentially specifically exclude any sites from being proxied that we choose to if we want to do that. In my case, I'll just leave that blank just for simplicity, and I'm going to hit OK. And I'll close this preferences window. Now you can see I'm in my OWASP server 10.0.2.4 as we've been working. And now if I scroll down, and I'm going to look at this training application called WebGoat in this example. So if we click on this, again, we're in our typical browser. We see our loading bar here, and we can see the proxy over here on the left-hand side. And now you'll see I need to select this forward button in order to get this traffic to work. So it looks like the proxying is working just as we would expect. And by the way, if we go in our normal Burp Suite window here, we can toggle this on and off with this intercept on button. So if I actually toggle that off, that's going to stop intercepting traffic, and it's going to allow our browser to work normally. So with this WebGoat application, we can log in with the default settings guest as the username and guest as the password. And you can see that takes me right to this training application where we can start WebGoat. Again, I don't have to forward through this because I've turned my intercept off. So I wanted to give you a look at that and how you could configure your local browser to take advantage of that. Once we land here in WebGoat, we can see a menu of labs as we've seen with our other tools such as Mutilidae. So let's go under our access control flaws and we'll just select one of these. I'll try this stage 3, which is bypassing data layer access controls. So with this particular login screen, again, we have a list of employees here, and with WebGoat, the password is going to be the first name of the employee. So this particular employee is named Larry as the first name, password Larry, and that will get us logged in. Now, once I'm logged in, you'll see that I'm able to select from a list of employees here to view the profiles. If I click the View Profile button, it takes me to the profile for the employee. Now, if I go back to the list staff, we have access controls in place at the data layer, which are controlling which employees I'm able to see profiles for. So I can only see, in this instance, my own profile, the profile that I'm logged into. And you can see that I have personal information in here like social security numbers, phone numbers, and more. So you can see exactly why we want to limit this. We don't want this information shared with other staff. So let's go back to list staff here, and I'm going to log out. And this time I'm going to begin intercepting. So I'm going to go over into Burp Suite. I'm going to turn my intercept on. I'm going to log in. Again, we're assuming that we've been able to obtain some sort of login credentials on this system, whether that's a legitimate employee or maybe a default account, or maybe we've done that through password tools. So now with my intercept on, I need to forward through everything so that this page loads correctly. So let's do that. And when I do that, you can see I'm brought back to the page that we've seen previously where I'm able to view my profile. So let's click the View Profile button, and we will likewise forward through that until we're able to see our profile. So let's go over into Burp Suite now, and let's look at the HTTP history for the traffic that we've captured here. So if we begin digging into this, we see a post message towards the bottom that's of interest to us. And the interesting information that we see in here, what jumps out to me is this employee ID. You see the employee ID is 101. Now, if we go back through this, of course, we're going to be able to see more details, things like the actual password that we used. We see that as Larry. We see the action was login, and again, we see the employee ID. So let's go down here to this post message for actually viewing the profile. We can right click in this request data, and let's send this to our repeater where we're able to try repeated things in here. And let's go ahead and send the original request in there. This is not going to render super well, just because of the way that this particular application is encoded. It's a bit jumbled up. Let's see if I can stretch this window out, if that will help at all. If I close my inspector, and it helps a little bit. Let me stretch it just a little bit more so that things aren't as jumbled. So we do get a little bit of jumbling there, but again, you can see the first name is Larry, last name is Stooge. We see the relevant information in here. Now, let's say we want to try and view a different employee's profile than we have access to. What can we do? Well, again, this employee ID definitely jumps out to me, so let's give that a try. Let's say maybe 105. Let's send that in. And now you'll see that I have a different profile here. First name is Tom, and we have their personally identifiable information. So let's take this, let's copy our request data. We can right click in here. We can request in a browser. I'll choose original session. We can copy this. We can go back into our Firefox browser and let's paste this in. Again, we need to go over to our proxy and our intercept tab, and we do need to forward through these because we're still intercepting traffic. So we'll forward through all our requests and we'll see what we have once we're finished with that. And once we forward through everything and get to the end of the information that we need to forward, you'll see that we're presented exactly what we saw in our repeater output. We see a different employee's information. So we see their own phone number, their social security number. We see a credit card in there. We see that this is a co-owner. So this is a high-level employee. So we have effectively bypassed access controls at the data layer. We've been able to access data that we should not have been able to access from a typical user account. So this is an example of how we would bypass access controls. Now, there are all kinds of different restrictions that we can do. We can test different HTTP methods that we've looked at, things like get, post, put, delete, and more. If we're able to alter these commands and send those to the web server, it's possible that we're able to do actions that we shouldn't be able to do. Things like viewing unauthorized files or even deleting unauthorized files from the database itself. Now, we've mentioned the proxy feature here in Firefox where we've implemented this. And if we go back to those preferences and take a look at those settings, of course, we're proxying things through a local proxy, but sometimes there also may be access controls in place for geolocation. So maybe certain countries are blocked. Proxying in this manner is another way that we might be able to bypass geolocation access controls. Maybe we can find a free proxy server in the country that's not being blocked by geolocation access controls. Or we can even use things like VPN services to do that. Next, let's look at attacking session management. When a user is validated with a web application, they're given an associated session ID, what we refer to as a cookie. If we're able to obtain these session IDs or to mimic a session ID or even to predict what a new session ID may be, then we can begin our own session with the web application without being authenticated. So we've already looked at setting up Burp Suite as a proxy in our local Firefox browser. So we're all set there. We're going to use that. And let's go ahead and look in WebGoat. We've been using WebGoat previously. This is the main WebGoat menu. And the option we're going to look at here, these are our labs on the left-hand side. We have session management flaws, and we have hijack a session. So that's what we're going to be looking at in this case. So let's go over to Burp Suite. At the moment, our intercept is off, so let's turn that on. And let's go back to WebGoat, and let's load our hijack a session page by clicking on that. You'll see that our traffic is intercepted over here. So let's take a look. We'll forward through this, and we'll take a look at what we can see in our HTTP history side of things in Burp Suite. So we see we have these get methods where the session cookie is being set. And with WebGoat, we can see in our request data, we see that here at the bottom. Our cookie is named weak ID. So this is the actual session cookie that is being set when we access this web application. So what we want to do is we want to try removing this weak ID field, then forwarding the request in order to force the web application to present us with a new cookie. And we'll see if we can alter this information or learn anything from that. So let's go back to our intercept feature. By the way, if we want to clear out our previous HTTP interception history just to clean things up, you can right-click in this window where we have our HTTP history, and we can choose to clear the history, and we will confirm that. And that just kind of cleans things up for us so that we understand more what we're working with. So let's go back to our intercept window, and inside of WebGoat, we'll click this link again to load the hijack a session page. And in Burp Suite, we do see that capture over here in our window. So what we want to do is let's go ahead and actually delete this session cookie, the information that's related to that. And once we delete that, let's forward our edited request over to WebGoat. And now let's look in our HTTP history and see what we have. If we click on our first get method, we can see here this is the original request. Notice at the bottom, we're told this is our original request. We can actually click this drop down for anything that we've edited in real time as we've captured that with our proxy capture, and we can look at the edited request. So here we see the version that we actually sent over. And again, just to give you a look at those and compare those, you can see the original request had the weak ID listed inside. The edited request does not. And if you look at the response to this on the right-hand side, you'll see that we have a weak ID listed over here. So in response to this, we were given a new session ID cookie. Notice this is the set cookie field. Let me highlight that for us so that we can point that out better. We have a set cookie field, and we've been presented with a session ID cookie. So the set cookie field is an HTTP response header that's used to send session cookies from the server over to the user. The cookie is stored by the user on the client side, and that's presented to the server. The cookie is referenced by the server for each request that a particular client makes in order to validate their session. Now, one weakness that may be present in web applications is weak cookie randomness. That's what we refer to as low entropy. Entropy meaning that we have lack of predictability. So low entropy means that we do have some predictability. In other words, generated session cookies should be random enough to prevent situations where attackers could guess or even predict session IDs for valid sessions through analysis. Now, the tool in Burp Suite that we can use for taking advantage of this or for testing for low entropy is the sequencer. The sequencer can help to analyze the randomness of data, including things like session cookies. So in our edited request tab over here on the left, let's right click inside here and let's send this to our sequencer. Then along the top, we'll jump into our sequencer and we'll take a look at what we can do with this. You'll notice that the sequencer tab recognized the session cookie. We see this listed in the cookie field down here. So it's already recognized what we're probably interested in trying to sequence. So we have a Start Live Capture button. Let's click on that, and you'll see our sequencer running along the top here. And what it's doing is it's actually repeatedly sending data over to this web application. In other words, it's repeatedly making session requests and it's gathering session data. Now, remember that we didn't need to log in order to obtain a session cookie. We did not log into the web application itself. We're obtaining these cookies simply by accessing the page. Now, we can let this complete, or if we think we have enough data, we can actually stop the live capture. So let's go ahead and do that. I'll just stop that where we are. I'll confirm that. And when we stop that, or when this completes, we're going to see a summary of the analysis. If we actually look at the character level access, this is where we're going to see some interesting features in regard to this particular web application. The character level access is going to give us some information about where we might or might not find randomness. Now, if we look at our session cookie, let me move this window over just a bit. So you can see on the left-hand side, we have our original session cookie. And here we have significance levels in this bar chart. If I scroll down just a bit so that we can read the bottom of this bar chart, you'll see that these are the charted character positions for the session cookie. You can see that our session cookies have 19 characters. So this bar graph is a measure of the degree of randomness for any particular character. In this output, notice we have a spike in positions 4 and we have a spike in positions 17 and 18. So this starts the character count at 0 with binary counting. So position 0 would be the very first character in our cookie. If we look at our actual cookie, we'll see that the first 5 characters are separated by a dash. So that makes sense in regard to what we're seeing here. We're seeing 1, 2, 3, 4, 5 characters, which are the first 5 numbers we see in our session cookie. And it looks like that 5th character, the last character before the dash, we see a spike in that position, in position 4. And likewise at the end, particularly in the last 2 characters of this number, we also see a spike there. So this analysis essentially tells me that it looks as though we're only changing the last number before the dash and the last 1 or 2 numbers at the end of the session ID. So that's valuable information to know. In order to further analyze that, let's go ahead and save our tokens. If we click the Save Tokens button, I'm just going to save this to the desktop, and I'll name this sessions.txt, and I will save that file. Now let's view this text file, and I'll just do that from our terminal. Let's change into the appropriate directory where I have that located: home, user, desktop, and if we do an ls command, we can see our sessions.txt file located here. So let's say cat sessions.txt to take a look at the contents of this text document. Now you'll notice that some of these are a bit out of order. They're not exactly sequential as they're listed here. So we can actually sort these. We can say sort sessions.txt, and this will perform some alphanumerical sorting for us. Sorting is going to help us to recognize any sort of patterns that we might see. And you can see that we have session ID. Let's start looking through these. We have 270, 24, 25, 26, 27. We have a gap between 27 and 28. We have 29 through 38. So what we may find of interest are any areas where we're seeing gaps. Gaps in the numbering here for this session ID, those can indicate potential valid session cookies for legitimate users that may have already been handed out by the server. So these are what we want to take note of. And we see a gap between 27 and 29. And likewise at the end, at these last two characters, we see a gap between 61 and 67. So it's possible that we have a valid session at 270.28 and somewhere between 61 and 66. So let's test this out. Let's go back into our Burp Suite, and we can close out our sequencer here. We don't need that anymore. Let's go back into our proxy tab here and our intercept page, and just to get some fresh information, let me first clear my HTTP history here. So we'll right click, we'll clear history. I'll go back to interception, and once again I'm going to click on this to reload our page, and let's go back into Burp Suite to take a look at the information that we've captured here. So we've captured an instance of the get command that has a session cookie set. Let's right click in here and let's send this to our intruder. We'll go to our intruder tab along the top, and let's take a look at our positions that are inside here. And as we've looked at before, you can see that this automatically recognizes areas where we may want to have a payload. Let's actually clear this out. And back in our terminal, remember we suspected there may be a gap in here between these two. So let's actually copy this value. Let's go into our intruder and let's paste a different value in for the session ID. So now we have manually set this particular session that we looked at in our output as the session ID. Now again, we suspect a potential session at 28. So let's go back into our intruder and let's change this 27 value to 28. Now we also suspect that this session should lie somewhere in between 61 and 66 for the last two characters. And we can actually do that by setting this as a payload. So we can also set payloads for particular sections. So if we highlight these last two characters and we add this as a payload position, then we can go into our payloads and we can do this in an automated manner. Now with this particular payload, we want to change our payload type to numbers. And when we do that, you'll see that we're able to sequentially go through a set of numbers instead of having to manually enter in those payloads. So the numbers we're probably going to want to try are 61 through 66. So in the from area, we'll say 61, we'll say 266, and we'll say we want to do that in a step of 1. In other words, we want to increment that by one number at a time. And let's start our attack by clicking the Start Attack button in the right. And let's see what happens. So that attack has completed, and you'll see again, if we look at the lengths are going to clue us in on what was or was not successful. And I don't believe this will render quite well just because, again, of the coding. So let's maximize this and try to do the best we can. Expand this just a bit. So this, even though it's jumbled up, hopefully you can tell that this is just our typical page. This is our typical login page. The same way with the payload of 62. Now we have a different length on 63. So let's click on that and let's try to render that. And let's see what it tells us. And I'm not sure how well you can see this, but once this does render, you can see, again, it's a little jumbled here, but at the bottom, we can see a congratulations message saying you have successfully completed this lesson. So this is a message from WebGoat letting us know that we were successfully able to predict and use a session ID that we were not given. And you can see the payload for that was 63. So the correct session ID that we were able to predict was 27028. And the last two characters were 63 for this particular session. So that's a look at how we can use some sequencing to try and predict session cookies to give us access to places that we shouldn't have access to, particularly valid user sessions that we're not authenticated for. Let's look at injection attacks, and we also refer to these as input validation attacks. This can include things like SQL injection. That's what we most commonly think of when we think of injection attacks. We're attempting to insert malicious strings of input, maybe into a website's login form, in hopes that this malicious syntax will give us unexpected control of the web application. Now, although we can certainly use automated tools to attempt this, if we're familiar with SQL language and common SQL injection commands, we can do that directly from the web application user input area that may be presented to us in a web browser. So first, let me point out that there are many examples online where you can find SQL injection commands. If you're not familiar with the syntax, then you can find lots of cheat sheets, such as the one we see here from Portswigger. Portswigger is the company that has developed Burp Suite that we've been looking at quite extensively. So this SQL injection cheat sheet will show you some common SQL injection commands that you can try out in your lab. And you can test these against the applications in our broken web app vulnerability server if you'd like to do that. You can also easily find other examples of this through a quick search of the internet. Let's go out to another resource that we haven't looked at yet. I'm going to open my Firefox browser here in Parrot OS, and you can see that I'm on a website called testphp.vulnweb.com. So this is another purposefully vulnerable tool that we can use for our testing. This particular website is actually hosted on the public internet. So you can go out to this website directly and start testing against PHP. PHP, by the way, is one of the most popular scripting languages for web development, for web applications. It's free and it's open source and it runs on the server side, so the code is executed on the server. And that's a common way that we interact with SQL databases. SQL databases being structured databases where we have data inside. So let's talk about some ways that we can perhaps leverage vulnerabilities here and test this out. And the first thing we're going to do is I'm going to open up a new tab and I'm going to use Google search to try and find instances here of databases that may be hosted on this website. So I'm going to use a qualifier site : that tells Google to search for instances of a certain website. And if I go back into my vulnerable website, I'm actually going to copy this URL and let's paste that into my search bar. And I'm going to add an additional thing to this. I'm going to put a space after this, and I'm going to say PHP ID equals. And I'm going to hit enter to search for that. This is a technique called Google dorking, or in other words, Google hacking. We're leveraging search engines to try and find places that may be vulnerable. And we see some search results pop up here for us. The ID that we have listed at the end, when we're accessing a certain database, we might see this PHP ID equals followed by a string of characters. This is common even if you look at something like Facebook. If you're looking at a Facebook profile, this will likely be tagged at the end of someone's profile. So this would reference a profile in the database and it would pull that each time. And that's what we're looking for. We're looking for any instances of databases that we have. And we do have some search results available. And if we scroll down, we can see lots of those here. Actually, let's take this second one. This one looks like it's in a different language. So let's take this second one and we can click on that and it'll take us out to this particular website. But this particular website address is what we're interested in. So you can see this takes us to a site, testphp.vulnweb.com/artists.php. So let's make some assumptions here. Let's make some assumptions that since this is a database of artists, what if we say $artist equals 1 and we hit enter? Well, you can see that this takes us to a sample page for a particular artist. What if we say artist 2? That takes us to a different artist. So using this Google search, we've figured out a scheme for how this database might be organized. So let's take what we know here and let's try this out in our terminal. Let's jump over here in a terminal and look at a tool called SQL Map. SQL Map is another one of our open source penetration tools that are included here in Parrot OS. And this works by automating the process of trying to detect and exploit any SQL injection vulnerabilities that might be in place, and it helps us to enumerate certain databases. So to run that, if we say SQL Map, and if we want to see information about the syntax we could use, we can of course say -- help. I'm going to clear this off, and I'll show you how we can use this. We can say SQL Map -u, that is going to indicate a target, and in our case, the target, let's go back to our browser momentarily. You can see the target here. Let's copy this just to make things a little easier for us. We'll copy our URL and we will paste this inside of our terminal. And at the end, we can use -dbs as our switch to try and discover any databases. And once we hit enter, we can see our SQL injection attack beginning. It shouldn't take too terribly long to run, so we'll give this just a moment to run and see if it discovers any information. And pretty quickly, we do see that we have discovered two database names. We have one called AccuArt and one called information_schema. We also see that this web server is operating as Linux Ubuntu. We see the web application technology listed here as well, the PHP version. We see we're running backend MySQL 5.0.12. So we've gotten some information from this database. Let's see if we can continue to enumerate this more. So we know about two databases currently. Let's arrow up to our original command, and let's see if we can enumerate one of these databases. Let's see if we can find the tables of the database. To do that, we can say -d, and we want to call out the database that we're targeting. Remember, we found two of those. We found AccuArt and information_schema. Let's try AccuArt, and we will say tables, because we're trying to enumerate the various tables of the database. Let's hit enter. We'll let this run and we'll see what we find. And now that our output is complete, you'll see that we found 8 different tables inside of the database. We found artists, carts, category, featured, guestbook, pictures, products, and users. Now, it's also helpful when we are trying to perform injection attacks or enumerate SQL databases to know the columns as well. So let's arrow up, and instead of tables, let's say columns, and let's hit enter, and we'll let that complete. And now you see our output here. We see our different columns and tables. So we see things like the name, which is text-based. We see the artist name at the top. We see the artist description and the artist ID. So again, more good information. And if we scroll up, we're going to see even more columns. And what we're looking for is something that is interesting that might give us access. So near the top, we see some columns that are definitely interesting. Things like address, we see email, and this one, password, and this one for username. Those are definitely both that are interesting to us. So let's see if we can potentially dump out the contents of these column values. Let's arrow up. And so we are still targeting the database with a capital D, AccuArt. Let's say -t, because the table we want to use is users. If we go up towards the top, the way we know this, you'll see that all of these tables have names. This particular table is named users. So this table contains information about users on the platform. And scrolling down, similarly, we see tables like pictures. So this is information related to photos that may be in this database, and so on and so forth. We see a table named guestbook that contains messages, the senders, and the timestamps. So this table at the top that we discovered, which we deemed to be most interesting, is called users. And we're hoping this contains username and password information. And most likely it does based on the things that we see here. So we'll go back down to our output. The table name is users, and we'll say -c for column. The column, if we scroll back up, notice the column name for that is uname. We see that here, username. So we'll say the column that we're trying to enumerate is uname, and we'll say -- dump to attempt to dump out the contents. Let's hit enter and let's see what happens here. So you can see in our output, we were able to dump the contents. It looks like in this particular sample database, there's one entry and the username is test. So we can do the exact same thing if we scroll back up to our original output for the password column as well. We have the same table. Table is users. The value here is pass. So let's try that. Let's go back to our terminal at the bottom. We'll arrow up, and this time we're still using the table users that we see here, but for the column, let's say pass. That was the name of the column that we saw, and we'll try again to dump that, and we'll hit enter, and we'll see if we get any results. And we do have one result here. We see one entry for the table users. The password value looks to also be test. So it looks like we have a user named test with a password named test. So let's try this out. Let's go back into our browser here, and let's go to our main page. Let's go to your profile, and this will prompt us to log in. So let's try test. Let's log in. And sure enough, we do see our test account listed here. We were able to successfully access this database. So that's an automated method for doing that, and there are other tools we can use for that. As I mentioned, we can also do this manually if we're familiar with SQL syntax. So this is our original URL that we were testing against. And one of the common ways that we can use to try and find SQL injection errors is to try to input strange characters. And one of those would be an apostrophe. So let's put an apostrophe at the end of this and hit enter. And when we do, we get back a SQL warning. Now this is bad design. And of course, this is purposefully bad design in this particular test lab. But we don't want to see this because this actually gives us information about the database, and it lets us know that this website is vulnerable. Ideally, this would not return a warning. And again, if you're familiar with SQL syntax, we could try other iterations of commands at the end of this. If I do something like order by 3 dash dash and I hit enter here, this is a way that we can view a particular column number. So we enter a number after the order by command, which in my case was 3, and we can see if we have any output in the database. So we do have at least 3 columns in this case. If we went up to, let's say, 10 and we hit enter, we get an error. So we can continue to do that with trial and error to try and discover just how large that is and how many columns we have. So 8 didn't work. 5 doesn't work. 4 doesn't work. So it looks like 3 is the key number. It looks like we have 3 columns in this particular database. So that's an example of how we could do that through a normal user input on a website. Again, there are options for doing both ways. Both are effective, and both are tools you would want to have in your toolbox. Now, obviously, we didn't dive into SQL syntax deeply because that's a huge subject that could encompass its own course. But if you're interested in SQL injection, that's definitely something that you could spend a long time studying and learning a lot about. And again, I would recommend that you reference things like SQL injection cheat sheets and other online resources to learn more about how you can test out common SQL injection vulnerabilities. Application logic flaws come from misconfiguration of the coding and also the incorrect implementation of a web application. SQL injection attacks are something that apply here, and also things like cross-site scripting. Now, SQL injection and cross-site scripting are more higher levels of this, and they're a little easier to achieve. Outside of those two methods, these can be much more difficult to identify. We don't really have automated tools that we can scan for these types of things. This is something that's generally just going to require a lot of trial and error. So as an example of this, if you think about going out to maybe Amazon.com, and we think about how we typically complete an order there. We add something to our cart, we finalize the order, we put in our payment method, and then we get a confirmation and delivery details. So if there's some sort of flaw in the logic and the way that that application flows, maybe we would be able to bypass the payment part and go straight to the delivery details and be able to place a confirmed order. That could be achieved through numerous methods, maybe some sort of code injection or another method that we've looked at. But again, I'll reiterate, these are very hard to detect, typically because they require a lot of time and a lot of trial and error. So as a simple example of this, we're here in my OWASP machine. Let's go out to our WebGoat training application. One of the tools that we have available here to us is this WebGoat password recovery. So we can actually put in a username here if we don't know, a login to the system, and we can request a password. We can recover that. So let's just try a couple of things. Let's say guest, and if we hit enter, you'll see we're told this is not a valid username. Please try again. So let's say guest 1, same thing, not a valid username. Guest 2, same thing, not a valid username. So we're trying this over and over and over. And with good design, there should be a limit on this. There should be some sort of lockout. Maybe we're identifying the IP address that these requests are coming from and we're shutting those down. Let's try a legitimate user here. We have a legitimate user here called WebGoat, and you'll see that the recovery method here is a secret question. It asks us what our favorite color is. Now, I happen to know that the correct answer to this one, based on the WebGoat documentation, is red. So if I submit that, it returns back the username and the password. That's an example of application logic flaw. This is not a good password recovery option to be built into an application. It's a dangerous approach. And let me show you why that is in this particular case. If I go back to the forgot password page and let's try admin. I'll hit enter. Now we do see that this is a valid user. So that's the first flaw in this logic, is that it validates whether or not we have a legitimate user before we're ever asked a security question, instead of asking both of those at the same time, or instead of requiring an email address. So we can essentially brute force the usernames that are found in this database by just trying various usernames over and over and over until we get one that seems to work. That brings us to the secret question page. And if we try our color red, of course, that's not correct. We see incorrect response. Please try again. What if we say blue? Incorrect response. Please try again. Yellow? Incorrect response. So you see how this is letting me continue to try things, and eventually, if I try green, that works. We have the username admin, the color for the security question was green, and it spit out our password back to us here. So again, very, very bad logic. It's better to do something like email a password recovery to the email that's attached to an account. That's what we commonly see, so that we can bypass these sort of logic flaws. So this is just a simple example. Again, these are hard to detect out in the wild, but when we're talking about application logic flaws, we're talking about misconfiguring the application in a way that opens us up to vulnerabilities. Let's expand a bit here on shared environments as well. Now, it's very common these days for third-party service providers to be used as hosts for web applications. Places like Amazon Web Services or Microsoft Azure as a couple of examples. The service providers themselves provide infrastructure for the web applications and the web servers. So it's a much more cost-effective method of deploying these, and it's also easier to stand up and tear down web applications on demand. So there are many good advantages to using a shared environment. Now, just like with normal environments that may be hosted locally, there are things that we need to be aware of in regard to vulnerabilities. As we mentioned, there is a shared underlying infrastructure. So if there are vulnerabilities inside of the underlying infrastructure, whether that's the hardware itself, the network, or the operating system, then that can allow an attacker to move laterally through that infrastructure and perhaps attack multiple environments that may be hosted there, multiple organizations' web applications. Another common way this may occur are through remote access attacks. An attacker may check to see if there is a remote access mechanism in place, and if this is a third-party service provider, that's probably going to be the case. Remote access is necessary for the clients to be able to connect and configure their web services and their web applications, as well as their database. And they want to be able to do that from a remote location, because obviously, as a third-party provider, these clients aren't going to be on site. They're going to need remote access. So an attacker might check whether the remote access mechanism that's being used has any unpatched vulnerabilities, or whether there are any configuration errors from the service provider's side. If there are, those can potentially be exploited. That can allow them to gain their own remote access or to do things like capturing credentials that they can use to log in legitimately into the web application and into the databases. They would also check whether or not the access privileges are separated properly between those shared clients. So for example, if there's some sort of configuration error in place that would give customers a higher level of access to the shared environment, maybe like shell access rather than normal file access, that's a big problem. That can allow attackers to potentially gain their own shell access and to access the sensitive underlying files, operating systems, and data being stored on the web server. And of course, if they are able to access one single organization's web application, then there could be the ability to pivot, depending on how they were able to do that. Let's suppose they have gained shell access to one particular web application inside of a shared environment, then they can try to launch attacks from there laterally to other hosts inside of the shared environment. And when they are attacking between applications, they would use many of the methods that we've already outlined here. They may try to attack other access controls, authentication schemes, or even use things like SQL injection attacks. When a web application sends requests to a database server, they use connection strings. So in other words, strings of data that describe the resources being requested. Now, these can potentially be altered for malicious purposes with malicious instructions in order to perform various actions. And this exploits the way that the applications actually connect to the database itself. When our applications connect to a database or to a data file, then strings are sent from the application to the underlying application server and eventually to the database to request data. And that connection string, again, contains the information that we need to know in order to establish a connection to a specific resource that we're requesting. Now, there are many different ways to write a connection string depending on the underlying structure that we're using. And there are basic formatting rules for the information that's inside of that. If you're familiar with coding at all, these are all string values, so there are no specific data types here. So we see an example of a typical connection string here on our screen. Now let's take a look at an example of the exact same string, except this time at the end, you'll notice we have an additional parameter, and that parameter is encryption equals off. So as you can see, these parameters are separated by a semicolon, and the attacker has been able to inject a parameter by adding a semicolon and using a separate encryption parameter at the end of this. An example like this would mean that the attacker has voided the encryption system. This is what we call connection string injection. We also sometimes refer to this as connection string pollution. And these attacks are used to gain control in some unauthorized way. We can also use these types of attacks for credential hijacking, where we are using parameters here to bypass authentication measures that may be in place, essentially giving us access to the data without ever authorizing. So that's a big reason we would see connection string attacks used. Now, most commonly when we're thinking of database connectivity, we think of this in terms of denial of service attacks. This is the most common way that we see this implemented. We often see connection pool denial of service attacks. What is a connection pool? SQL Server does use connection pooling, and what connection pooling offers very simply is better performance, more stability, and higher availability. So if you think of every time someone connects to our database, it consumes a resource. It consumes a physical channel like a TCP/IP socket or a port. If we're using TCP, we have a source and destination, and we have a handshake taking place, and so that connection is no longer vacant. Now imagine we have a web application and we have many users who are constantly connecting and deconnecting from the database connections. If we didn't use connection pooling, that could create a situation where we can possibly exhaust all of our potential connections, and that would lead to an application crash. It would lead to a situation where users could not connect to the application. So the way that application pooling works is we have a pooling manager. Again, that's something as an example built into SQL Server, and the pooling manager keeps connections alive for a certain number of seconds. That way, if someone disconnects and later on they come back, there is a cached connection that's kept alive so that the connection can be reused instead of establishing a new connection to the database. First, this saves time because we don't have to reestablish a connection. And of course, it saves resources. We're protecting our pool. We're protecting the number of connections that we have available. So with denial of service attacks against connection pools, one way we might see that happen is a high number of connections being automatically sent, maybe a high number of queries being sent out to a database. If you think of ASP.NET as an example, the maximum number of allowed connections that they have in a connection pool is 100, so it's limited. There's a finite amount of those, and the timeout by default is 30 seconds. So if we've configured some sort of automation, whether that's through Burp Suite or some other tool, to go out and make database requests, and we run hundreds and hundreds or even thousands of those, and we do those in a very quick manner, then we can potentially cause a denial of service issue because no one else will be able to connect to that. We would have taken up all of the application ports available for database connections. So by targeting connection strings to the database, we're targeting the system that actually forms a link between our web application and the database. So we may not be necessarily breaking the web application, we might be breaking that connection itself. And if we're using injection attacks, we can sometimes pull unauthorized data out of there for things we aren't allowed to see. And again, typically we see this used as a denial of service tactic where we try to exhaust a resource pool. Let's look now at how we can affect multiple web application clients. If we can somehow alter the behavior of the server-side applications, then we have the ability to affect any other users who may try to access the web application. So let's take a look at cross-site scripting as an example of this. Specifically, we're going to look at an example here of what we call stored or persistent cross-site scripting. That's where we're storing a malicious script on a server so that it gets executed each time a client accesses a resource. So let's go back in here in our OWASP and let's go to WebGoat once again. We'll log in with guest. Let's start WebGoat. And on the left-hand side, you'll see we have a cross-site scripting section. I'm going to look at this stored XSS attack. So here's just an example of how this works. So what we're going to do, this is a typical message board or maybe a comment section of a website. And we're going to see if we can do a stored cross-site scripting attack where we store code onto this database. And I'm going to write a script that will show an alert message, just as an example. Now, the actual actions would most likely be malicious and they would be quiet. But just so that it's very obvious, that's what I'll do here. So let's go in here and let's create a title and let's call it very important. Hopefully that will lure some users into clicking on this. Next, in the message box, let's actually write some scripting. And I'm going to use JavaScripting here. So I will say script language equals JavaScript type equals text/JavaScript. I'll close that out, and then I will say I want to create a pop-up alert, again, just so that that's very obvious here for our purposes. You probably wouldn't want to do that in the real world. You want to be quiet, most likely, or maybe you wouldn't. It just depends on how you're trying to do this. So for the alert, let's say danger. We'll close that out, and then we will close our script. And let's submit that and see what happens. So now you'll notice in our message list, we have a message that says very important. So hopefully any other user that would come to this message board or to this comment section, this could be maybe on a blog or a website. And if they click that, look what happens. They get the pop-up saying danger. Again, I made this alert just so it's super obvious what is happening, but that's an example of how we can store code in a persistent manner for cross-site scripting. So you'll notice even if I leave this page, if I go back to a different page, let's go here, and I go back to cross-site scripting, my stored cross-site scripting attack, my message is still in place. So this is persistently stored, and it does still work. Now, the end user's browser has no way of knowing that this script should not be trusted, and it will execute the script. In this case, that's just a pop-up message, but that could be really anything. We can use that to completely rewrite the contents of the HTML page. to access the user's cookies, session tokens, or any other types of sensitive information that may be saved in their browser. Now, the reason this is successful is that this was incorrectly configured from a programming standpoint. The programmer should have configured input validation, which would not have allowed the cross-site scripting attack. Our input boxes should be configured not to recognize any sort of coding or scripting if we want to be safe from this. We've mentioned already that we have two general types of web services available. We have SOAP and we have REST or RESTful services. RESTful services have been what we've primarily examined already here in regard to attacking web services. We've looked at using some of these HTTP verbs, and these are a modern replacement for XML-based SOAP services. Even though we technically consider SOAP to be a legacy system, we do still see that in place. So let's talk about some ways that we can attack SOAP services. SOAP services, as we've said already, those rely on XML, Extensible Markup Language. And Extensible Markup Language was developed originally by Microsoft, and that carries data and it stores data in plain text. So if we have a database that's using XML, that means that the data inside will be in plain text. It allows programming languages to communicate with one another, and that uses something called XPath that we'll talk about more in just a bit. Now here you can see a very simple example of how a web application may store user data inside an XML document. As you can see, this is very easily readable and interpretable by anyone. If an attacker can figure out a way to perform an injection attack and inject additional XML code, then they can often gain access that they may otherwise not have. They may be able to even inject their own user account. So let's jump over here into our instance of WebGoat that we've been using. And in the left-hand menu, let's look under the section for injection flaws. And from there, we can choose XPath injection. So this brings us to a login page. Now, when we have databases built in XML formatting, when we query those databases, this is performed with what is called XPath query language. So the XPath is essentially the flow that the data is taking. As we enter user credentials here, those are carried back to the server in order to verify the credentials, and then it redirects us to the appropriate screen in the case as we see here, or the appropriate data will be returned back to us. What we can do here is perform a classic injection attack, and we call this an XPath-based attack or an XML injection attack. Now, this looks basically identical to a SQL injection attack. In fact, the syntax we'll use is exactly the same. But SQL injections, of course, only work with SQL language. XPath will work with any database using XPath as the query language. Additionally, another consideration is, and the reason that we see this used less and less, is that SQL agents have the ability to implement access control. Just like access control with a router, if you're familiar with that, this can help to lock down things. We can lock down user permissions, we can lock down the actions that they're able to perform, and which data they're able to see, change, or delete. XPath doesn't have this mechanism, so that makes things a bit easier from the attacking perspective. Now, you'll see that when we land on this page, we're given some login credentials that we can get into this with just so that we can see what it does. So let's log in with Mike, password test123. I'll hit enter, and you can see the information returned back to us from the database. We have an account number, and we have a salary figure here. Now, if we want to try XPath injection, we can try a very old trick here, one that's been around for quite some time. This is a very well-known exploit. This is one of your classic methods for SQL injection. And we can also use this for XPath injection as well. What we can do here in the username box, we're going to start with an apostrophe, or a single quote, in other words. This is a character delimiter to delimit strings. So this is a way that we can commonly test to see whether or not strings are properly terminated or escaped in a web application. If this character gets accepted, that means that they're not being terminated correctly. And any additional string that we add afterwards, whether that be SQL or XML injection code, those would be accepted. So we're going to follow that with an or statement, and we're going to say, quote, 1, close quote, equals, quote, 1. And we're going to go down into this password box and we're going to put in the exact same input. We're going to say quote, space, or quote 1, close quote, equals quote 1. Let's hit our submit button and let's see what happens here. And we get a message letting us know we've successfully completed this lesson, so that's probably good. And of course, you can see at the bottom, all of our information has been dumped back to us. So the 1 equals 1 statement that we used, all that is a true statement. We have a true statement in the middle because 1 does equal 1. So this true statement means we want to select all of the values from the table that this is referencing, and we want to return those values back for our own viewing. So again, this is a classic way that we can perform XML injection attacks. Now, we can, of course, get more complex here as we enter more complex code if we have the ability to send in things like additional spoofing commands. We can send in actions in XML format where we can delete files, we can create new users. The possibilities are vast here. One more helpful tool that I'll point you to here is a tool called XML Spy. This is built by Altova, and you can see their website here. This is a way that we can actually create XML-based web service applications using, among other things, XML. You can see that it also supports JSON and some other things, XPath, XQuery, SOAP, and so on. So this is a development environment that might be helpful, especially if you're interested in XML injection attacks. You could download a free trial of this and you could play around with this editor and learn more about what XML does and some of the formatting in that. Let's wrap up our section on web applications by discussing some security considerations. Now, some of these we've touched on throughout this section, but it is worth summarizing those here at the end and adding a few new ones in. As ethical hackers, we should be aware of these considerations, and we should be able to recommend these as necessary. And those are going to depend on the findings of our assessments. So that's why it's good to know these. If we find a particular thing that's a vulnerability that could be potentially exploited, we should have some suggestions for our clients to implement. So we want to be aware of open source vulnerabilities. Now, open source tools have lots of benefits. They're very cost effective. They're lightweight, but they do expose you to potential vulnerabilities because they're not always supported by a vendor. In other words, you won't be getting frequent updates from that. So when we're using open source software of any kind, we want to be sure that we're continually monitoring that for any vulnerabilities that may appear and any updates that do happen to be put out for those. Again, typically we can't rely on the vendors themselves to be serving out updates in a super frequent manner, so just be aware of that if you're using any open source solutions. Also, we want to have well-defined assets. An asset is defined as anything that's valuable to our organization. So the contents of our web application servers, those would certainly be assets. Now, if we don't know what we need to secure, that makes it really hard to secure it. So we want to know exactly what assets make up our applications and our software, whether that's the underlying software itself or whether that's the data inside. We want to make sure that we're taking everything into consideration when we're implementing security. And of course, limiting user access. The principle of least privilege is something that we've already mentioned in this course, and that means only giving users the access that's absolutely necessary in order to perform their job duties. And that's certainly true with web applications. Web applications are typically available over the public internet. Another reason we want to be super controlled with the level of access that we give the everyday user. We need to determine who actually needs access to a particular resource. We should create access rules if we're using something like SQL that's built into SQL. And we want to make sure also that these access privileges remain up to date. If we run across a situation where a user no longer needs access to a certain resource, we should remove that. If we have an employee leave the company, we should remove their access. All of these things are important considerations for limiting user access. We also want to be sure that we are performing ongoing penetration testing assessments. And this is where we come into play as ethical hackers. There are certainly automated tools to make this much easier for the everyday user, even those who may not be as experienced in network security or in ethical hacking, but this is where we really get to shine. Automated tests can catch most things, but there's really no replacement for a good experienced pen tester. So it's important to use both of these methods. We want to use automated tools and we want to use our manual skill set to continually test against our web applications. And again, we want to do that in a frequent and ongoing manner. We want to do that in a scheduled manner. We also want to make sure that we are regularly patching and updating our software and our systems. This is one of the most effective ways to close up security holes. So why would we bother trying to spin our wheels and trying to solve problems if we have a patch or an update that will fix that for us? So it's important to do that. And not only that, but to have a regular patching and updating plan. This is something else we've talked about. We should be sure to test any patches or updates in a sandbox or in a lab environment before we deploy those into production. Certainly anytime we're upgrading to new versions of software, we want to do that in a test lab before we release that into our production environment. And of course, proper logging procedures, something else we've touched on quite a bit here. We have to have log data if we're going to have any sort of incident response plan that's effective. At the end of the day, no matter how good we try to prepare, there are always things that could happen. We could always be hit with some sort of incident. If we don't have the knowledge of our logs, then we may be very powerless when it comes to understanding what happened and to correcting what happened. We also want to make sure that all of our input data is being effectively validated. We've looked at a lot of examples of this with input validation attacks, where we've looked at web application forms that we were able to insert data in there that should never have been able to be inserted. If we have a username box, only usernames should be accepted. We should not be able to input any sort of scripts or other coding. So input validation would include things like the character lengths, the size, and so on. Another good recommendation for your clients are to consider bug bounty programs. We see this with all kinds of Fortune 500 companies. They have bounty programs where they actually pay folks to find bugs or vulnerabilities in their web applications. This is very common. There are websites like bugcrowd.com where, as a penetration tester or an ethical hacker, you can actually sign up and you can go and work on some of these bug bounties and try to find vulnerabilities and earn money for yourself. So this is a good way to get some outside eyes on that. And of course, we should consider automated security tools. It's easy for us to overlook things from time to time, so it's good if we can automate things like updating and patching. There's always a factor of human error, so anytime that we can leverage good automation that works, that's going to be a plus.